So what we're going to have a look at today is the different types of functions we can work with. And this is where we're going to actually start having a look at a formal definition of a function. It's a bit weird that we only do a formal definition in grade 12 because we've been working with functions since grade 9, essentially. We're going to have a look at a formal function, how we can identify if a graph is a function or not. And then as of Monday, we're going to start having a look at the grade 12 stuff, which is now talking about inverse functions and specifically the inverses of exponentials. That's sort of where we're heading. All right, but to start us off, can anyone tell me, and you can put in the chat or you can unmute yourself, what is a function? So when I say, oh, we're doing a function set, what do I actually mean? What is a function? Anyone? Okay. Well, a function is essentially a rule or a formula that allows us to describe a relationship. Now we look at relationships that exist between two variables or two values. And the variables that we obviously know when it comes to our functions is x and y. So x is our input, y is our output. We want to have a look at what relationship exists between them in order for us to then potentially graphically represent it. We could potentially algebraically solve for different characteristics of our function, like an x-intercept or a turning point or stuff like that. But essentially, at the base of it, a function is this rule, this formula that we have. Now, in order for something to be a function, you can only get, or rather, let's rephrase this. In order for something to be a function, a single input can only give a single output. I'm just going to write this down and then I'll explain what I mean. Okay, so what I mean by that is, and I'm just going to say it again, for a relationship to be a function, we can only get a single output for every input. So for example, if you substitute in the value of x, we should only get one y value. Okay, so if I substitute in, I don't know, whatever 2, my corresponding output, I should only ever get one potential value. I can have a situation where two different inputs give the same output, like a parabola. So if you think of a parabola, and here's our x-axis, we can have two different x values with the same y value. That's fine. But in terms of the relationship between input and output, for a single input, I should only get a single output. I shouldn't be getting multiple outputs. And we'll see why this is in a second. And essentially, it means that we're not dealing with a function. So in order for us to test whether or not something is a function, so to test whether or not they do have a single output for a given input, we use what we call the vertical line test. And it's really not very sophisticated at all. And I'll show you as we do some examples, but we use what we call the vertical line test. If it passes the vertical line test, it means that we have got a function. Sorry, something strange just happened. Okay. Now, if we think about it, and I'm just going to use a parabola again. So here's my parabola. There it is. It is a function because for one single input, I get one single corresponding output. I'm not getting multiple different outputs for a single X input. One input, one output, it's a function. But if I wanted to test whether or not it's a function, what I would do is I would take my ruler. Oh, okay, apparently I'm going to take a triangle. I would take my ruler, place it vertically along my function. And essentially what the vertical line test is if you move this vertical line, it should only ever cut the graph once. So you can see no matter where I put this line, no matter where I move this line, it is only ever cutting my graph once. And that is essentially what the vertical line test does. It should only cut your graph once in order for your graph to be a function. If it intersects more than once, then we do not have a function and we have something else. We'll chat about that in a second. All right, so I know this sounds like a slightly weird definition and like it's a lot of inputs, outputs, one, how many should we have, etc., etc. But the easiest way to determine whether or not something is a function is through the vertical line test. As long as that vertical line only cuts your graph once, you have got a function. If, for example, we had something like a circle even. So let's say I drew a circle. That is a function. Let's try that again. This circle represents a relationship between variables when I plot it on a Cartesian plane. There's an X and a Y. But what you see now is that my circle cuts my vertical line twice. So for one single input, let's pretend that's 2, I'm getting 2 different outputs. I can't have that if I want specifically a function. And so in this case, a circle would fail my vertical line test. And so a circle is not a function. And we're going to chat about what it is then in a second. But before I move on, I just want to make sure that everyone is fine with this definition, because like I say, it's a lot of words to basically say if a line cuts it once, it's a function. If it doesn't, it's not. So can we just get a thumbs up if we're okay with this definition of a function? We are going to have a look at some examples and so on. But like I said, I find it quite confusing because it's so many words to basically just say one input, one output. Thank you for the thumbs up. I did see another one. I can't remember who now. Morgan, thank you. Simtanda, thank you. All right, well, if no one shouts at me to stop, I'm going to assume that we're okay. Excuse me. Right, so if we have a look at sort of just some values here to get a basic understanding of what's going on with our functions. Here we've got 2 sets of values. We've got a domain value and a range value. Very basically put, I've got an X and a Y value. So these are all my X values. These are my Y values, because remember, domain is X, range is Y. Now, these are all input and output values. So these are representing ordered pairs of a relationship between X and Y. So what I want you to see in this first example is that every single X value only has one single Y value. So what I mean by that is this -2 only has an output of 1. This 4 only has an output of 6. This 5 only has an output of 7. This 3 only has an output of 9. So for every single X input, I've got one single output. Oops. All right, now when we have one input, one output, and that's how it exists for our entire relationship, function. Right, now, an example of this would be something like a basic straight line. So if we drew our straight line, there we go. For every single x input, I get one corresponding output. X input, one corresponding output. There is never a double up. Okay, so these are your graphs where for every one input that you have, you get one single output. Now, there's a couple of these types of graphs. So like I've already said, we get straight line or linear graphs. This would be a one-to-one function. Hyperbolas would be one-to-one functions. Exponentials would be one-to-one functions. And we are going to learn about logarithmic graphs, but log graphs would also be one-to-one functions. If you think of an exponential, for example, here's my exponential, 1x, 1y, 1x, 1y, 1x, 1y. One value, one input corresponds with one output. That is what we call a one-to-one function. And it's one of the types of functions that we need to be comfortable with. Okay, if we go and have a look then at the second group of values, again, we need to see that over here, my input -2 has an output of 16. My input 0 has an output of 4. And my input 1 has an output of 4. So there's something a bit different there. Two different inputs have the same output. Now, we've actually already discussed this example. But think of your parabola. Okay, here's my parabola. Let's actually draw it according to what we have here. Golly, Miss Molly. My input of 0 has an output of 4, but my input of 1 also has an output of 4. And this is essentially working off the symmetry that exists in a parabola. So for parabolas, we can have two different, so here are my two different input values giving us the same output. And that's the symmetry of our parabola that we often speak about when we talk about functions. Now, this is absolutely fine to have. There's one input, one output. Just because one input has the same output as another, we're not getting a situation where this 0 value is giving the two outputs. That's not the situation. The situation is two different inputs is giving me the same output. So two different inputs, one same output. That is fine. We've got no issue with this. If we think back to our vertical line test, I draw my vertical line. No matter where I move that vertical line, it's only ever cutting my graph once. So it passes the vertical line test. It is a function. It just so happens that it is a function whereby different inputs can have the same output. And because of this fact, this is what we call a many-to-one. Right? If you think about it, many different x's have one output or the same output. Again, there's nothing wrong with that. We have got no issue with a many-to-one function. Oopsie, sorry. It still passes our vertical line test. And so we have a function that we can work with here. Right, if we have an example of the relationship over here in 3, this is now where things get a little bit iffy. So I've got the input -2 gives me an output of 16. But now this is where my problem is. This single input is giving me two different outputs. I can't have that. That's like the circle situation, where one input is giving me two different outputs, and that is not a function then. So we've got a bit of a conundrum there that we need to consider. So when it gets to these situations where we've got one x value, different y values, what we have then is not a function. What we have is called a relation. There's still a relationship. It's just not specifically a function, because remember, a function, 1x, 1y, passes the vertical line test. One single input gives us two different outputs, not a function. I can't work with that. So this would be something like, let's just make that a touch smaller. This would be something like your circle. If you plotted a circle on your Cartesian plane, there would be, and any sort of random irregular shape or irregular graph where it sort of comes back on itself and you end up with a vertical line passing through 2 points. Now you're going to see this again when we start to talk about inverse functions, but let's have a look. All right, just quickly jumping back to 2 because I didn't actually say anything here. These many-to-one functions examples are your parabolas. And I don't know how many of you have started calculus or have looked at cubic graphs, but a cubic graph would also be an example of a many-to-one function. A cubic graph looks something like this. There's different variations of it. So that's a cubic graph. And so what you see is that, for example, two different x values give us the same output. So that is a many-to-one function. Right, if you want to determine whether it's a one-to-one or a many-to-one, this is now where we use our horizontal line test. Horizontal. So for example, if you consider, let's say, for example, your exponential, if you now drew a horizontal line, if it only cuts it once, it's a one-to-one function. However, if you consider something like, again, let's go with your parabola, if you draw a horizontal line and it cuts it more than once, we have a many-to-one function. Many x values for the same y value. If it does not pass the vertical line test, so the up-down one, like I said, we don't have a function, we have a relation, and then we're not going to perform the horizontal line test because the horizontal line test only tells us if it's one-to-one or many-to-one, and that only exists when it comes to functions. Okay, so there are a couple different sort of classifications of a function that we can have. We can have, is it a function or is it a relation? And if it is a function, is it one-to-one or is it many-to-one? And that's where we can use our horizontal line test. So I'm just going to hang 10 there in case you want to take a screenshot. Again, just give me a thumbs up if you're feeling okay with the definition. Like I say, a lot of words to decide whether or not something is a function, but you'll get the hang of it as we go along. Please also just remember, grade 12s, ask me questions as we go along if something's confusing you. Like I say, I know it's a lot of language to start off with and terminology, but we'll get the hang of it hopefully once we do examples. Yeah, I think I only saw Morgan giving me a thumbs up there, so I'm going to assume we're all okay. All right, so guys, I do have what is a relation here, and we can write it out, but basically just bear in mind a relation is just a set of ordered pairs to coordinates. And okay, so my words. A relation is basically just a set of ordered pairs, and they can be in any shape. You could have a group of ordered pairs that give you a weird sort of shape like that. That's still a relation. It represents a relationship between x and y. It's definitely not a function because it fails my vertical line test by passing through twice, but it is still a relationship. Same as a circle, still a relation, still expressing a relationship between x and y. It's just not a function because it's cutting through twice. So the second something is failing your vertical line test, all you actually have is a bunch of coordinates. That's it. There's nothing special about those coordinates that we have. So if you want to take a screenshot with it, there you go. But otherwise, we're going to have a look at some examples now of identifying whether or not something is a function, and then what type of function it is. Alrighty, so let's have a look at some examples here. So we want to state whether or not the following are functions or relations, and then what type of function are they if they are a function. So this is where we would grab our ruler, and you can quite literally even just draw a line if you want, and we will draw our vertical line. So here's my vertical line. And all I want to do now, because remember, to determine whether it's a function or relation, we use a vertical line test. All I want to do is check that no matter where I move this vertical line, it's only ever cutting my graph once. And we can see that it's cutting once, it's cutting once, cutting once, cutting once. No matter where I move this line, it only ever cuts my graph once. And because it's only ever cutting my graph once, what that means is that we have got a function. And if we want to determine specifically what type of function, we can now use our horizontal line test. So if I draw my horizontal line, there it is. No matter where I move this horizontal line, it's actually only ever cutting my graph once. Now remember, when your horizontal line only cuts your graph once, what you have is a one-to-one function. Because one x value, one corresponding y value. That's it. Right, so to determine whether it's a function, vertical line test, to determine what sorry guys, I have no idea what happened there. I do apologize. Okay, let's get this back on the road. Okay, here we are. So I want you to have a look at question B, and I want you to decide, is it a function? Is it a relation? And if it is a function, what type of function is it? Amanda, nice. Simtanda, nice. Okay, guys, exactly. Vertical line test. There's my vertical line. Now it looks like vertical line. No matter where I move this line, it's only ever intersecting my graph once. So it means it is a function. And if we want to determine what type of function, as both Amanda, Simtanda, and Lydia have now said, we take a horizontal line and really just use your ruler. No matter where I move this horizontal line, it's intersecting my graph twice. So as long as it intersects more than once, we have what we call a many-to-one function. Because there are many x coordinates for one single y coordinate. That's what a many-to-one function means. All right, let's try C and D for me. You guys can try both of them. So is it a function or is it a relation? And then what type? You can put it on the group. Just remember to label C and D. I'm not seeing any answers just yet. Maybe you're trying C and D. Right, let's have a look. So if we go to question C, here's my vertical line. And I need you to be very careful with question C. No matter where we move it, it's actually only ever intersecting with my graph once. Okay, it's still once, it's still once, it's still once. It gets quite close to touching twice, but it never actually does. It actually only ever intersects with my graph once. It's tight, but it is only ever intersecting with my graph once. So because it only ever cuts my graph once, this is in actual fact a function. If we want to determine what type of function, here's my horizontal line. Right, if I look at my horizontal line, in some places it cuts it once, in some places 3 times. But either way, it is cutting my graph more than once at certain places. If it only ever cuts it once, it's a one-to-one. But here, because it's cutting my graph in certain places multiple times, this is a many-to-one function. Now remember I showed you what a cubic graph is earlier. This is actually a cubic function. And so we do cubic functions when we do calculus a bit later, but it is a function. It does pass the vertical line test, and it is a many-to-one function. Many-to-one because it cuts my graph multiple times for the same y value. Right, if we have a look at D, so here's my vertical line. What we now notice is that my vertical line, no matter where I'm placing it, except what the turning point, is cutting my graph multiple times. Now I need to be careful. So because my vertical line is intersecting more than once, it is now a relation. It is not a function. So we have now a relation. Some people like to say it is a one-to-many relationship because one x coordinate, many y coordinates, but there's no need to go that step further. It is a relation. It's not a function. There's no need to classify further because it's not a function. Right, so really importantly, C is a function. D is not a function because of that vertical line test. Right, we have also done an example with the circle, but let's see if we remember. Quickly decide for me, is it a function or relation? And if it is a function, what type of function is it? Nice, guys. Okay, I think we've all got it. So vertical line test, we can see it's cutting twice. So unfortunately, this is not a function. This is just a relation. And you don't bother with the horizontal line test. Horizontal line test is only if it is a function, what type of function is it going to be? So if it's not a function, we don't do the horizontal line test. All right, so, oh, golly. I know it's a bit small, but if you want to take a screenshot of those four, five, please do so. But that is what a function is, how we identify it, how we determine or how we decide what type of function it is. That's it, vertical and horizontal line test. So take a little 2-minute break, have a stretch, run to the bathroom if you need to, and then we're going to have a look at just a past paper question, because again, we need to revise this stuff. On Wednesday, we are going to start talking about inverse functions, which is really exciting. And so we'll bring in this information that we've just learned when we do our inverse functions on Monday. I think I said Wednesday. I meant Monday. If I did, I apologize. Right, guys, but like I said, take 2 minutes and then we'll carry on in a bit. Alrighty, guys. So let's have a look. So the reason I also wanted to do this specific question is because when we start to look at inverses, we focus a lot on the inverse of exponentials, and so we work quite a lot with exponential graphs. So it is really important for us to be able to understand the basics and go back to the basics of our exponential graphs that we learned in grade 11 and grade 10. And so once we have this knowledge and once we are comfortable with exponential graphs, hopefully log graphs will be a lot easier to deal with, a log graph being the inverse of our exponential graph. Okay, but let's have a look here. This is now from last year's grade 12 paper. So this is what they were asked last year. So it gives you a good idea of sort of the standard and the type of question that you're going to be asked come June, come mock exams, come the end of the year. So remember I said to you on Monday, your functions questions are generally questions 4 to 6, sometimes 4 to 5, depends on who's setting the paper and how much function questions they're asking, but generally 4 to 6, you can expect your functions. So we've got sketched below is the graph of f of x is equal to 2 to the power x minus 4, for x is an element of negative 2 to 4. A and B are respectively the y and x intercepts of f. All right, so before we even get to the questions, which we can't even see yet, let's just establish what's going on. So hopefully, because of that x in the variable, we know we're working with an exponential graph. And what's really important here is that this statement, this x element of negative 2 to 4, this is actually a restriction on my domain. So if you go to the graph, you can actually see that. You can see that your graph doesn't extend past that open dot, nor past that closed dot. The domain has been restricted. Right, now the open dot is because the 4 is not included. And we know that because of the round bracket. And the closed dot down here is because the negative 2 is included. And we know that because of the square bracket. So there's a restriction on my domain, something to just bear in mind, because why else would they do it? So we need to be careful. We then are told A and B are the x or the y and x intercepts respectively. We can see that on the graph, we've got no problem. If we now go to the actual graph, what I want you guys to take note of is the fact that here's my x-axis and here's a dotted line down at the bottom. And so what that means is that we have an asymptote. If we have an asymptote, our graph has shifted either up or down. And in this case, it's a shift down. So we'll probably have to deal with that in a second. However, if we go back up to our actual equation for f of x, it is 2 to the power x minus 4. So we know that this is a shift 4 units down. So this asymptote is at y equals negative 4. So all of this information I have gotten just by looking at my graph, by reading the information I was given, and now I have a fair amount that I can work with. Okay, now that we've got that, we can move into the questions. So the first question is asking me to write down the equation of the asymptotes of f. Already I know what the answer is because I took a little bit of time and actually just interpreted what I was looking at. I already know that my asymptote is at y is equal to negative 4. I don't have to do any thinking, any calculating, nothing. Because I've gone to my equation and I've said, okay, what does this mean? What is this telling me? And I've actually gone and interpreted my information. There's nothing else I need to do. That's it. If we then have a look at 4.2, it says calculate the coordinates of B. Now, guys, B, remember, is your x-intercept. So can someone remind me, how do we work out the x-intercept of any function? Nice, guys. Exactly. This is now where we make y equal to 0. So I want you guys to work out for me the x-intercept or the coordinates of B? I'm going to give you a minute or two to try. Tell me what the coordinates of B are. And guys, remember, obviously, because you're working with an exponential graph, you're going to have to deal with exponential equations. So just remember your rules for exponential equations. So sorry. Okay, so we are getting two different answers. One of them is correct, and we'll have a look now in a second. But make sure you double checking your work. Nice, guys. Okay, so we're making y equal to 0. So 2 to the power x minus 4 is equal to 0. Exponential equation. Exponential equation tells me I need to try and get my bases the same. So we're going to have 2 to the power x is equal to 4. And we know that we can write 4 as 2 to the power 2. Remember, once your bases are the same, the only thing left to equate is your exponent, because you've already made the bases equal. As long as this equation is true, bases must be equal, exponents must be equal. And so now we've got x is equal to 2. And so my coordinate for B is 2, 0. So those of you that got 4, just double check where you might have gone wrong. Just remember it is an exponential equation, and so we must solve it appropriately. Right, 4.3, and we did one like this on Monday, but 4.3 says, determine the equation of k, a straight line passing through A and B in the form k of x equals. So let's go up to our graph. I don't know why I said we did one like this on Monday. I think I'm losing my mind a little bit. So it says k is a straight line passing through A and B. So here's A, here's B. We need the equation of this line that's passing through both of those coordinates. Now we have just worked out that B is at 2, 0, and we can easily go find out what A is. Now, because AB is a straight line, we have the equation that we need to essentially find y equals mx plus c. We need to know m, the gradient, and we need to know c, the y-intercept. Now, my brain has stopped a little bit. We have been told to write in the form k of x equals, so k of x is equal to mx plus c. And if we just look at our straight line, A is going to be the y-intercept, okay? But A is also the y-intercept of f. So we can easily go work out what the coordinate of C is by finding our y-intercept. Now, remind me, how do you find the y-intercept of any function quickly? For any function, how do we determine the y-intercept? Nice, guys, well done. Right, so y-intercept, we now make x equals 0. Like I said, the y-intercept is the same for both the exponential and the straight line. So we know f of x is equal to 2x minus 4. Quickly go and find for me what the y-intercept is. Nice, guys. Good. Okay, so if we substitute in x is 0, remember any value that isn't 0 to the power of 0 is 1. So this 2 to the power of 0 is 1 minus 4. And so y is equal to -3. So that means my coordinates of A are 0, -3. So what I now know, if I quickly go back up here, is the y-intercept of my straight line, which is great. So now I know that y is equal to mx minus 4. And so the only thing left that I have to solve for is m. Now you have got options of how you want to do that. We also know that b is a coordinate on my graph. And so because I know it's a coordinate on the straight line, I can substitute it in to solve for m. So if I do option 1 and I substitute in b, I would have 0 is equal to m times 2 minus 4. And so 4 is equal to 2m, which means m is equal to 2. So k of x is equal to 2x minus 3. That's option 1. It's the easier of the two options in my opinion, but I'm also not sure how many of us would think to substitute. I feel like a lot of us are so used to using the gradient formula that that's probably the thing that we would do. Now, there's nothing wrong with that. So if you do go ahead and use the gradient formula, option 2 would be, okay, you know what A is, and you know what B is. We can now substitute in m. So m is y2 minus y1 over x2 minus x1. So this is 0.1 and this is 0.2. y2 is 0 minus 3 over 2 minus 0. Can I not do maths here? Interesting. Why am I getting two different answers? Oh, guys, because I'm a little bit stupid here. We're clearly nearing the end of term. Sorry, your y-intercept is -3. Thank you, Sientanda. And so m is equal to 3 over 2. Right, there we go. If we go back to our gradient formula, we've got minus 3, so positive 3 over 2. So f of x, k of x is equal to 3 over 2x minus 3, not minus 4. Sorry, I don't know where I got minus 4 from. As you can see, it's the same equation. So whether you choose to use your gradient formula, whether you choose to substitute in the point that you know and solve for m, it makes absolutely no difference. It is completely up to you how you choose to do it. All right, but either way, we get the equation of k of x. It's a straight line. And like you can see, both are the same. You get the same answer. All right, so just for purposes of screenshotting, because I've made this very small, let's just take a screenshot at this point. So only 2 more questions, and they are quite short questions. Right, so let's wrap up these last 2, and then you guys can have a look at your quiz that you got. So if we look at the question 4.4, this is asking us to calculate the vertical distance between k, so the straight line, and f, the exponential, at x equals 1. So if we go back up to our graph, x equals 1, it's going to be some random little point, but x equals 1 is about here. So we want the distance between these two graphs here. So where x is equal to 1 on the straight line and where x is equal to 1 on your exponential. Now, guys, whenever you are asked for a vertical distance, a really useful formula to remember is top minus bottom. Now, when I talk about that, I'm talking about your y values. If you can work out what your top y coordinate is, so in this case, the top y coordinate is on the straight line, and your bottom y coordinate, you can then just go and subtract the 2. Now, we have got an equation for both k and f. So we want to work out where or what the value of y is at 1 for k. So 3 over 2 times 1 minus 3, which gives us a half. And we want to do the same thing for f of x. So we're f of 1. That would be 2 to the power 1 minus 4, which gives me negative 2. So now I know if I scroll back up to my graph, sorry, negative a half. If I scroll back up to my graph, this y coordinate over here is at negative a half. This y coordinate over here is at negative 2. I now want the distance between the two of them. So the top graph was a straight line, minus a half, minus the bottom graph, which is 2. There's my top minus bottom. And so it is, oh golly, it is half a unit, guys. Clearly no one is on top of things today. 1.5 minus 3 is 1.5. Okay, so really important formula to remember is top minus bottom. Once you know what your y coordinates are, like I say, you quite literally just take the top one and subtract the bottom one. And to find your y coordinates, that is merely through substitution of whatever the x value is. So once you know specifically what x value you're talking about, all you're going to do is sub it into your equations, top minus bottom. That will always give you your vertical distance. And remember, so our bottom was a negative. When I sub it in, remember what happens. It's going to become a plus. And that's why our distance will always be positive, as it should be. Your distance should always be a positive value. Alrighty. Last one. Whoops. Write down the equation of g if it is given that g of x is equal to f of x plus 4. So let's think about what this is saying. F of x is 2 to the power x minus 4, as it currently stands, so the original graph. This plus 4 that we've now been given here is saying move up 4 units. Now, if I already have moved down 4 units, if I move back up 4 units, it means that I'm sort of cancelling out the shift anyways. And so g of x then just becomes 2 to the power x. Obviously, you can substitute in and you can say g to the power x is equal to f of x, which is 2x minus 4 plus 4. And there is the cancelling of the shift up or down. So that was just to test whether you understood that that addition of a constant is an up-down shift, and so what actually happens. All right, but I'll do this. Take your screenshots of these last two equations.